Swayam Prabha. Digital India. Educated India.
So, last class I was discussing about the 1D ground response analysis, and I was discussing about the linear approach, and then I derived that response for a uniform undamped soil on rigid rock. Okay, so this is my bedrock. This is the bedrock and this is the uniform soil layer, this is ground surface, and we got that shear stress at the ground surface by doing this differentiation with the horizontal displacement that we got that we can get from this equation. And now we assume that at the surface obviously the shear stress is 0 and shear strain is 0. Now, so that means this term is 0, so this should be also equal to 0. Now, if this is 0, now this is only possible, or if I take this is outside, that g I k e to the power I omega t, and this is a e to the power I k z is equal to 0 here, because it is the surface, z equal to 0, minus b e to the power minus I k z equal to 0. Okay, and now this is z equal to 0 means e to the power 0, which is equal to 1. So, finally, I will get that my g del u 0 t by dz, that will be equal to g I k, then it will be a minus b into e to the power I omega t. So, that is equal to 0, because your shear stress equal to 0 at z is equal to 0. Okay, that you know we are getting at the surface, the displacement at the or shear stress at the surface. So, it is only possible, this condition that this whole term is 0, it is only possible if A is equal to B. It is only possible, or it is possible or satisfied if your A is equal to B. Now, if we put A is equal to B, so finally the response at the ground surface, or the response we can get by using this boundary condition, that u z t, that is equal to A e to the power I k z minus plus e to the power minus I k z divided by 2 e to the power I omega t. How it is coming? Because I know that my cos alpha is and from this I know that cos alpha e to the power I alpha plus e to the power minus I alpha divided by 2. Okay. So, actually how this equation is coming? This equation is coming is, you know, that our response at zt is equal to A e to the power I omega t plus kz plus b e to the power e to the power I omega t minus kz. So that I can easily write by this thing, that e to the power I omega t into e to the power I kz plus b e to the power plus I omega t into e to the power minus I kz. Now here a is equal to b, so it will be basically twice a if you take this is now later on I will take that twice a. Now you keep a, okay. A, if I take common e to the power I omega t, so then it will be simply, because this is a is also b, so e to the power I k z plus e to the power minus I k z. Okay, this is the expression. This is the expression. So that I can write twice a e to the power I k z plus e to the power minus I k z divided by 2 into e to the power I omega t. Here how we are getting, because my b is equal to a. That I have proved. So this, why I have expressed it in this form, because cos alpha is equal to e to the power I alpha plus e to the power minus I alpha by 2. So now this equation I can write simple 2a into cos kz, because this is alpha is here equal to kz, then e to the power I omega t. Okay, so e to the power I omega t, simple. So finally I can write that my u z t is 2a cos kz e to the power I omega t. So now this cos 2z, simply I can write that this is the amplitude. This is the amplitude, because if I express simple harmonic motion in that exponential form, then from there I can write this is simply amplitude. Okay, so this is the expression. Now here this can be used, defined as a transfer function. How I can write the transfer function now? The transfer function is f1, this case I am writing 1 because this is for first case, into omega. So that is called the transfer function. Okay, so that transfer function is equal to what I am doing, that this I am want to get the ground surface motion from the bedrock motion. So bedrock is at a depth of h and ground surface is at the depth of 0, z equal to 0. One is ground surface where z equal to 0 and bedrock z equal to h. So now if I put this amplitude, that this will be 2a, this is the ratio between the your displacement amplitude at z equal to 0 and at z equal to h. So that is the transfer function. So from the bedrock I am transferring it to ground surface. So now that means here I can, or I should write in this form also, that first write it in. So this will be at u max, maximum displacement at z equal to 0 at any time t, z max at z equal to h at any time t. Which one is the h? So this is the h, thickness of the soil layer. So that is equal to h. Clear? So now this is the maximum displacement, means this is the displacement amplitude. Maximum will be when this is the maximum, u max will be this one, this displacement amplitude. So this is displacement amplitude at z equal to 0. So, that means it is at the top, divided by displacement amplitude at z equal to h, that means at the bottom of the soil layer and top of the soil layer. So, now what is the maximum displacement? U max displacement amplitude at z equal to 0. So, this will be simply from this equation 2a, this cos, if I put 0, is it why this is not the h, this will be j itself, this will be z, this is kz. Later on I will put the value. Now in the general equation I should write this is z. Now if I put z equal to 0 at the top, then the cos 0 will be 1. So it will be 2a simple e to the power I omega t, and this will be 2a cos k h e to the power I omega t. So I omega t 2a, that will cancel, it will be simple 1 by cos k h. So that is equal to transfer function. So now in this case your transfer function is equal to 1 by cos k h. Now the modulus of the transfer function, or this one you can convert it to cos, what is the k value? K value is given omega by Vs. So I can convert it to omega h by Vs. Now the modulus of the transfer function, that is f1 omega, that is modulus. Modulus of the transfer function is called the amplification function. Is the amplification function. What is that? That is actually root over the real part of f1 omega, that is square, plus the imaginary part. Square. Here it is only the real part square, so the same value will come here. Same thing will come here. Or 1 by simple cos kh. Okay, so 1 by will be cos kh. So similarly, you can see that your this modulus of cos omega h Vs, that cannot be greater than 1 at any condition. It cannot be greater than 1, because this is the cos value. So the cos modulus I am taking. So cos, any value of cos cannot be greater than 1. Okay. So it is definitely will be less than 1, or it can be 1. Maximum value can be 1. Okay. So that's why if it cannot be 1, so that the amplification function is always greater than 1. That means the amplification function is always greater than 1, which indicates, so what is this part? So this part cannot be, this part is always greater than 1. So that means I can see this value is always greater than 1. always, or equal. So, which is this? So, from this I can write that u max at 0t divided by u max as ht is always greater than equal to 1. So, which means that my surface displacement is always greater than equal to the bedrock displacement. Clear? Because u max at surface 0 is equal to surface will be always greater than equal to the displacement at the bottom bedrock. So, this way I can write, or if I draw it. So, now this kh term I can express by pi by 2 plus in terms of pi, because the maximum I want to get. So, maximum will be at pi by 2, because cos will be 1 at pi by 2. This cos will be your this multiplying amplification factor or the transfer function, that will be maximum at pi by 2, because cos pi by 2 will be equal to 0. So, that will be infinite or maximum I am talking about. Cos will be 1 at when cos equal to 0, but at pi by 2 this term will be maximum, because it is 1 by cos kh. So, if the kh, if I take pi by 2, that will be the maximum value of transfer function or modulus of transfer function. That will be, because it is 1 by cos. That is why I am telling that cos pi by 2 will not be the maximum. So, 1 by cos pi by 2, that term will be the maximum. So, if in that is the case, I can express it pi by 2 plus in pi, and then if I plot the modulus of transfer function, okay, with kh, then at 0 it will be 1, because cos equal to 1. Then at pi by 2, then if n equal to 1, this will be 3 pi by 2. If n equal to 2, it will be 5 pi by 2. If n equal to 4, it will be, if it is n equal to 3, it will be 7 pi by 2, and so on. Then 4, it will be 9 pi by 2. So, it will be maximum at these points, or it is maximum this value. So, that means here at this kh, different value of kh at this point. That means, if your kh is pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2, 9 pi by 2, it will be maximum. Then it will come down again. Again it will go maximum, again it will come down, and then again it will reach maximum, like this. Okay. So, that you can get the maximum value of the transfer function as modulus of transfer function, which indicates that at kh equal to pi by 2, you will get the maximum displacement of ground surface. Okay. And then, and always I have already discussed that the the ground surface or surface displacement is always greater than the or equal to the bedrock displacement. Okay. So, now finally, if I go to this curve again, so this is my bedrock motion, then I will go from frequency time domain to frequency domain by Fourier transform. So, that means that I will get the Fourier series, then I will get the transfer function, and then I have already discussed I will get the transfer function or the modulus of the transfer function. That transfer function for this particular case, uniform damp soil on rigid rock. Okay. So, then you multiply that transfer function with the Fourier series or bedrock Fourier series, then that will give me the Fourier series of the ground surface motion, and then if I do the invert of that inverting that Fourier series, then I will get the again from the frequency domain I will get to the time domain, and then I will get the again acceleration time history for ground surface motion. And I have already discussed that I can get the shear stress, shear strain at any point along the depth at any time, and provided I should know the G value, and here the G value is the G max because it is the linear approach. Okay. So, next case that I will discuss is that as I mentioned, I will discuss two cases. First, I will discuss the uniform undamped soil on rigid rock. Now, I will discuss the uniform damped soil on rigid rock. So, here I am not giving the response, I am directly writing the transfer function, because you know how to get the transfer function, because from the response transfer functions is basically the displacement amplitude at the top divided by displacement amplitude at the bottom of the soil layer. Okay. And bottom is the bedrock, top is the surface. Okay. And then now I am getting the transfer function F2 means it is the second case. Okay. So, this is the transfer function for this case. Transfer function, now here the transfer function for this case is cos omega h divided by Vs. This Vs h omega same as the previous case that I have discussed, into one plus I into damping ratio. Okay. And the modulus of the transfer function F2 omega, that is equal to the amplification factor or amplification function that is equal to 1 by root over cos square kh plus sin h square damping ratio into kh. So, this I can write in this form also, that is cos kh 1 plus I damping ratio. That is also possible, because we know that k is equal to omega by Vh. The wave factor is omega by Vh. Now, how are you getting this equation? Because that where your cos x plus I y is equal to actually root over cos square x plus sin h square y. Okay. So, from here I will get this expression. Now if sin h square y will be equal to y square for very small value of y. So, sin h square y is equal to y square or for small value of y. If we put that, then I will get that my amplification factor that will be equal to 1 by root over cos square kh plus, now this term will be, this is y, now this will be y square. If this is this y is very small, then this term will be the y square. So, this will be damping ratio into kh whole square. Okay. Or now if I convert the kh value in terms of omega and Vs, then I can write this is cos square omega h by Vs plus damping ratio omega h by Vs whole square. Again here also, if I put kh in pi by 2 plus n pi, again here also like the previous case, but here this the modulus of the amplification factor will never be infinity because of this damping part. This part will be equal to 0, but this part will never be 0, okay, because of the presence of damping. If the damping was not present, then again that will be the same case like the previous one that I have discussed. So, this will never a value of infinity because your damping will be always greater than 0 because it is damp case. So, that means here if I plot that again the amplification factor with respect to kh. So, here this is F2W mod, then again at kh equal to 0, this kh equal to 0, then this is cos 0, this will be 1, same as 1. After that, this is your say, now kh is replaced at pi by 2 n pi if n equal to 0. So, this is the your first kh equal to 0. Now, if your n is equal to 1, 2, 3, if you put the n equal to 1, 2, 3, then you will find that this part will become 0, okay, but this part that will increase. So, ultimately this F2W value in mod, that value will decrease because as you increase the number n value, n equal to 1, 2, 3, then this value will increase. First one is equal to damping ratio into kh, second or the pi by 2, then second part will be damping ratio kh into pi by 2 plus pi. So, this way this total this term will increase. When this denominator will increase, so obviously as we increase the kh value, then F2W mod that will decrease, start decreasing. So, the trend will be something like that, okay, then it will start decreasing this value. Like this. Okay, so for this is for any damping ratio, say 5% or any damping ratio you can consider. So, it will start decreasing with as kh increases. But in the previous case, there is a same amount of peak for pi by 2, 3 pi by 4, 5 pi by 4, 7 pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2. But here as this kh value increases, start decreasing because of this presence of this damping. Okay, so now this is my that linear case I have discussed, and one more thing I want to mention here, that what is the fundamental frequency. In my previous case, that for resonant column also I have to determine the fundamental frequency. So now this is the fundamental frequency is what? What is the fundamental frequency? That is basically the lowest natural frequency where maximum amplification occur. Okay, so now I can see that here the maximum amplification will occur with the lowest natural frequency, that I can say that kh, I am writing that pi by 2 n pi like this. So the lowest one, where the maximum amplitude will occur, the lowest one, that will be your pi by 2 into your, this is your, this is k will be omega by Vs. Okay. So omega by Vs, if I write in this form, that I will get that omega by Vs, I can write again. Either I can write kh equal to pi by 2, or here you can see that kh I am writing in pi by 2 plus n pi. Similar to the kh, I can convert to omega h by Vs. So that and then I can this omega h by Vs, that also I can write pi by 2 plus n pi, because kh replaced to omega h by Vs. So that is actually the cos term. So that is the cos kh or cos omega h by Vs. So that means this cos omega h by Vs also I can express in pi by 2. So in that case, this is the your first, I mean the lowest natural frequency. Well, the maximum amplification, the first lowest one will be omega h by Vs will be equal to pi by 2. That is the lowest. After that, the next one will come. So, but fundamental frequency is the lowest one. So, in that way, I can write that now omega 0 will be equal to pi by 2 Vs by h. So, that I can write here, that omega 0 equal to pi by Vs by h. Okay. Now, the period of variation, period of vibration corresponding to the fundamental frequency is called the characteristic site period. So, what is characteristic site period? So, that is basically the period of vibration corresponding to the fundamental frequency. Okay. So, that means here the characteristics time period Ts, a side period is T, that is equal to, we know that time period is 2 pi by omega 0. Okay. So, that will be 2 pi by omega 0, this will be 2 pi, omega 0 is pi by 2 into Vs by h. So, that I can write, this will be pi will cancel, this will be 4h by Vs, or that fundamental frequency, actually this is omega 0, the angular frequency. Now, the fundamental frequency, that will be 1 by Ts. So, that is basically Vs by 4h, okay, as Fn is 1 by Ts, or you can write that is equal to Ts is omega 0, 2 pi by omega, this will be omega 0 by 2 pi. So, omega 0 is pi by 2 Vs by h into 2 pi. So, this pi will cancel, this will be simple Vs by 4h. So, here you will get the fundamental frequency, that is equal to omega 0 is pi by 2 Vs by h, and Fn fundamental frequency, that will be Vs by 4h, and Ts characteristic side period, that will be 4h by Vs. So, what is V is the velocity of the CR wave and h is the thickness of this layer. Okay, so, now in this class I have discussed about the linear approach only. Okay, still I have discussed only the linear approach, and once we get the your transfer function, in the second case I got the transfer function. The similar way, by using this same process, I will get the ground surface, I will get my output motion will be our ground surface motion. So, from here also, from the bedrock to bedrock motion is as the input, I will get the ground surface motion, but the process is same, but here I will get the transfer function, and then I will multiply the Fourier series of the bedrock motion with the transfer function, then I will get the Fourier series of the ground surface motion, and then if I do the inverting of this Fourier series, I will get the acceleration time t for the ground surface motion. Clear? So, in the next class, I will discuss about the equivalent linear approach, and then I will discuss about the linear approach. Thank you.